Now we start with complex eigenvalues. Then afterwards we'll go to repeating or repeated eigenvalues. And then we tackle on how you can get eigenvectors that correspond to such eigenvalues. Note that for complex eigenvalues, they will come in the format of lambda equal to a plus minus bj, where a and b are real values. And then when we want to get the corresponding eigenvector, we just take one eigenvalue, which will be just a plus bj, and that will suffice, or should I say will be sufficient to give us the corresponding eigenvector, or should I say eigenvectors corresponding to these complex eigenvalues. So let's do some examples of such. Example 1, determine eigenvalues and eigenvectors for this matrix A. And as usual, we take the determinant of A minus lambda I and equate it to 0, and then thereafter we solve for lambda. From that matrix, we get 4 minus lambda into 4 minus lambda plus 9 equal to 0. And then it gives us the characteristic equation lambda squared minus 8 lambda plus 25, which results in lambda equal to 4 plus minus 3j. Please check my calculations and confirm. And then we take just one lambda, 4 plus 3j, and then we substitute. So when I substitute 4 plus 3j in place of lambda, I get negative 3j, negative 3 in the first row, 3 and negative 3j in the second row. Remember, we multiply by the column vector k1, k2, and equate it to the column vector 0, 0. Formulate the two equations. So the first equation is negative 3j k1 minus 3k2 equal to 0. And then the second equation is 3k1 minus 3j k2 equal to 0. So we take any of the two, or the simplest of the two equations, and try to get the unknowns. So I chose the second row, or the second equation, which gave me k1 is equal to j k2. And if I let k2 be equal to 1, then that means k1 would be equal to j. That's the eigenvector that I'm getting is j1. And then we split it up into real part and imaginary part. And note that j is 0 plus 1j, and 1 is 1 plus 0j. So that's how I got to split the two. Imaginary part becomes 0, 1, and then the imaginary part, the real part is 0, 1, and the imaginary part is j1, 0. I'm hoping that it makes sense. Please remember, j is equal to 0 plus 1 times j. So 0 stands for the real part, plus the coefficient of j is the one that goes into the second column. And then 1 stands for 1 plus 0 times j. So that means the real part becomes 1 and the imaginary part becomes 0. Here are some examples that we could also use to determine the eigenvalues and eigenvectors for that will give us complex eigenvalues, leading us to be able to determine those complex eigenvectors. Please attempt number 2, 3, and 4, and let's see how you will fare on this one. And then we go to repeating or repeated eigenvalues. When we say repeating or repeated eigenvalues, that's where we get, when we factorize the characteristic equation, we get lambda minus a value all to the power 2 or to the power 3 or more, depending on the size of the matrix. So that means a value is repeated. So here is an example. We've got matrix A, 3 minus 1, 9 minus 3. And then, as usual, we find determinant of A minus lambda I and equate it to 0. And then find the characteristic equation. I'm hoping that you realize that this equation yields lambda squared is equal to 0. So that means here you've got a repeating eigenvalue. So it's lambda equal to 0 and lambda is equal to 0 because it was lambda squared. So there are two values, but the two values are equal. So how then, when we get such a situation, do we get the corresponding eigenvector? So let's go for the first eigenvector. Note that this is a 2 by 2 matrix, so we are bound to have two eigenvectors, two linearly independent eigenvectors. We're still gonna do linear independence and linear dependence, but make sure that when you have a 3 by 3 system or a 3 by 3 matrix, you get three linearly independent eigenvectors. When you've got a 2 by 2 system or a 2 by 2 matrix, you are going to have to make sure that you get two linearly independent eigenvectors. So let's see how, from getting just lambda equal to 0, how we're going to get now two eigenvectors. We go the route that we already know, the matrix A minus lambda I multiplied by the column vector K equal to the column vector 0. And then in place of lambda, we substitute 0, of course, for this one, so there are no changes to matrix A. So we get those two equations. And in both equations, I get 3k1 is equal to k2. And then we let k1 be equal to 1. Note it's up to you. You could have said k2 is equal to 1, and then that would mean that k1 is equal to 1/3 of its k1 will be equal to 1 over 3. So it's still to work out. So it would mean in this case, if k1 is equal to 1, then that means k2 is equal to 3. And then that's what we get as our first eigenvector. Note that I said it's the first eigenvector because this is a 2 by 2 matrix. We have to have two eigenvectors. Now, how then do we get the second eigenvector? The formula changes slightly. Yes, we're still gonna have the matrix A minus lambda I multiplying the eigenvector, which is K2 in this case. But we are not going to equate it to a zero vector. We're going to equate it to the first eigenvector. So it's very important that your calculations for the first eigenvector be precise and be on point so that you use the correct values of your eigenvector in order for you to get the second eigenvector. So that means on the right hand side you have the first eigenvector 1, 3. Formulate the equations as usual, but remember you are not going to have 0 on the right hand side as we did first time. So now we have 3k1 is equal to 1 plus k2 from the first equation. Actually, I believe that both equations, they give us the same equation. Now you can let any of these values or these variables k1 and k2 be equal to 0 or be equal to 1. Note, the only reason why we do not say let k1 or k2 be equal to 0 is when you try to solve for the second variable, you discover that you are going to get a 0 again, because the eigenvectors can never be 0. So in this case, we let k1 be equal to 0, which suffices, because if k1 is equal to 0, then that means k2 will not be 0, and therefore our eigenvector will not be a 0, 0 vector. So if k1 is 0, we're getting k2 be equal to -1. Therefore, the second eigenvector is 0, -1. But you could have even said let k1 be equal to 1, as you usually do. If k1 is equal to 1, then that means k2 will be equal to 3 minus 1, which is 2. So that means you'll have 1, 2. So note that we mark according to your assumption. If you let k1 be equal to 1, then you'll get a different set of eigenvalues. Yes, a different set of these values for this eigenvector. So please make sure that you are authentic to yourself. If we say k1 is equal to 1, make sure that you do the right thing. K2 will be equal to 3 minus 1 will be equal to 2. So we have 1 and 2. But if you say 0, then that means k2 will be equal to -1. So we've got now 2 eigenvectors corresponding to 1 eigenvalue. Once again, we take the same eigenvalue, we get the first eigenvector. From the first eigenvector, we are able to get the second eigenvector by equating the left-hand side to the first eigenvector. So if our first eigenvector has been calculated properly, then we'll get the correct values for the second eigenvector. Please remember those two formulas. A minus lambda I times vector k is equal to vector 0. And then the second one is matrix A minus lambda I times the second eigenvector is equal to the first eigenvector, in order for you to get the second eigenvector. Now here are some examples that you may attempt to use those two formulas on to get the two eigenvectors. Please remember, it's always matrix A minus lambda I into the first eigenvector equal to a 0 vector. And then matrix A minus lambda I multiplied by the second eigenvector is equal to the first eigenvector, in order for you to get the second one for a repeated eigenvalue. This only works for repeated eigenvalues only and no other. Linear independence and linear dependence. We introduce you to vectors here, which are linearly independent or linearly dependent. There are two formulas or two definitions that we may use to check whether two vectors or even three vectors, if they are linearly dependent or linearly independent. If you can write one vector as a linear combination of the other two vectors, and then you can be able to calculate the constants and discover that not all the constants are equal to 0, then we say those vectors are linearly independent. So what it means is that if you can calculate all the constants, you multiply each of those vectors by scalars, equate that to 0, and solve for the constants. And then you discover that there is a value for one of the constants that is not equal to 0. Then it means they are linearly independent. But if you discover that the only solution that you can get is that all the constants must be equal to 0 in order for it to work, then we say it's linearly dependent. In layman's terms, what I can simply say is that if one vector can be written as a scalar multiple of the other vector, then it means they are linearly dependent. If you cannot write one vector as a scalar multiple of the other, then they are linearly independent. Now let's go for the example. We've been asked here, are these two vectors x1 and x2 linearly independent? Here we need to check whether x1 is a scalar multiple of x2. As we can see here, 4, 10 is equal to 2 times 5, 2, which means x1 is 2 times x2. In order for you to get x1, you multiply x2 by 2. Or in order for you to get x2, you multiply x1 by half. So that means these two are dependent on each other. So there is a scalar that is not equal to 0 that makes sure that these two are dependent on each other. So these two are linearly dependent. As an alternative, we use what we call the Wronskian. But for simplicity, we'll just simply say the determinant of a matrix that is comprised of the vectors given as columns of that particular matrix. So if you are given vectors x1, x2, and x3, for instance, you put those three vectors in matrix format. In the matrix, vector x1 goes into the first column, vector x2 goes into the second column, and vector x3 goes into the third column. And then thereafter, find the determinant. Now, if the determinant is not equal to 0, then the vectors are linearly independent. But if the determinant is equal to 0, then they are linearly dependent. Please note again, you take the vectors given, put them in a matrix format where each of the vectors is placed in a column in a particular order. And then thereafter, you calculate the determinant of that matrix. And if the matrix, that determinant gives you 0, then that means they are linearly dependent. But if the determinant of that matrix is not equal to 0, then we say we've got linearly independent vectors. Here is an example. Here we've been given x1 and x2. We're finding the determinant of these two matrices, of these two vectors. Put them in a matrix format. Then we get the determinant to be equal to 0. So that means they are linearly dependent. If the determinant is 0, linear dependence. If the determinant is not 0, linear independence. Here are some exercises ways as to show whether the given vectors are linearly independent or not. Please remember that whatever we do here, for all these three problems, we've got those exponential functions that are on the outside. So you multiply each of these inside. So you know when you multiply a scalar to a vector, you multiply the corresponding entries of that particular vector. So that means the first one, it will be 3e to the power t and e to the power t. The second one will be e to the power negative t, e to the power negative t. So you multiply each of the entries by those exponential functions given and then find those determinants. Now we go straight to diagonalizing matrices. Firstly, in order for us to attempt this, we have to introduce you to a diagonal matrix, which we call a spectral matrix. Remember, a diagonal matrix is a matrix that only has non-zero entries on the main diagonal and zeros everywhere. So if we have the eigenvalues of that matrix on the main diagonal and zeros everywhere else, then we call that matrix a spectral matrix. And it's a spectral matrix of A because the eigenvalues, they belong to matrix A or that particularly given matrix. Now, once you've got your eigenvalues, you have eigenvectors. If you are able to put the eigenvectors as matrices in a matrix format where each eigenvector corresponding to that particular eigenvalue is put on that column, then we've got what we call a model matrix. So that means the eigenvector corresponding to lambda 1 must be in column 1. Eigenvector corresponding to lambda 2 must be in column 2. Eigenvector corresponding to lambda 3 must be in column 3. So that means the model matrix must have the same order as you place the eigenvectors in it as the order given by the spectral matrix. So hence we are saying eigenvectors always correspond to the particular eigenvalues of a matrix. Now remember that eigenvectors always correspond to eigenvalues. So a model matrix is a matrix with corresponding eigenvectors of matrix A as columns. Now we are able then to say if you multiply the inverse of the model matrix by A, matrix A, and then you multiply it by the model matrix, you will get the spectral matrix. So that means you've diagonalized matrix A. So M inverse times A times M will always give you the spectral matrix. Also, if we just gave you the model matrix and the spectral matrix, and we ask you to calculate the original matrix, which is A, then you are able to use M times the spectral matrix times M inverse. Please note those two equations because they are of paramount importance. So when you diagonalize a matrix, you use the spectral matrix is always equal to M inverse multiplied by A multiplied by M. But when we have the diagonal matrix, which is the spectral matrix, and we have the corresponding eigenvectors, and you are looking for matrix A, then you are able to use the formula M times the spectral matrix times M inverse to calculate what A looked like. Now we come to exercises. The first one says diagonalize the following matrices. I would be interested in how you will be able to achieve that. And then we go to number 2 as well as number 3. Number 2, you've been given eigenvalues and eigenvectors. You're supposed to determine matrix A. And number 3, once again, you're asked to diagonalize the given matrix when the modal matrix has been given. Please attempt and make sure you do your calculations properly. Also remember, you may as well use your calculator to do those matrix multiplications by using mode and then choosing matrices, and then you load the matrices that you have. And when you want the inverse of a particular matrix, please you recall it by saying shift 4, and then you recall the matrix, and then you press the key that has got x to the power -1. Your screen will show. If it was matrix A that you are recalling, it will show mat A to the power -1. Know that your calculator will calculate the inverse of that particular matrix. Also, you may as well check when you've been asked to calculate the inverse of a particular matrix using cofactors and minors and cofactors, as well as the Gaussian elimination or the Gauss-Jordan elimination, or any other method that you've been asked to use. You may as well check your solution by loading that particular matrix on your calculator and check whether your answers correspond to what the calculator gives you.